In a previous video, I proved that the derivative of sine x is cosine x, and the derivative of cosine x is negative sine x. Remember that tangent is sine x over cosine x, so you could even use the quotient rule as another proof to prove that tangent x, the derivative of it, is secant squared x. Similarly, you can use quotient rule of quotient identities or reciprocal identities to help you find these remaining trig derivatives. If u is a function of x, that means we're going to have to use the chain rule. So the derivative of sine of u is cosine u times u prime. Cosine u, that would be negative sine u times u prime. That chain part is just deriving that inner function or that function of x and multiplying by that derivative afterward. Secant squared u times u prime, and so on. For number 1, we have secant x times tangent x. Because secant is 1 over cosine and tangent is sine over cosine, using reciprocal or quotient identities is not going to help us make this any simpler. So you may notice that you have a product of two functions. We'll call that f and g. The product rule is f dg plus g df. The derivative of tangent x is secant squared x. The derivative of secant x is secant x tan x. We have completely finished deriving, and now let's simplify if possible. Or you could write your answer in factored form. I thought maybe secant squared x plus tangent squared x would be a Pythagorean identity, but it's the subtraction of those. For number 2, we're taking cotangent of, is it x? No, it's not. So it's cotangent of u, some function of x. U is 3x squared, which makes u prime 6x. Y prime is equal to negative cosecant squared of u times u prime. I like to write this coefficient in the front. Let's try some problems where we're going to have chain rule within chain rule. We're going to start with the outside and work our way in. First of all, I'm taking sine of, is it x? No, it's cosine of root x. So that is a sine of u function. And y prime would be cosine of u times u prime, the derivative of what's inside. Cosine of something is not cosine squared. That's the composition of cosines. The derivative of cosine root x, is that cosine of x, or is that going to be a cosine of u? Well, since it's not just x, it's root x, then there is a u. That makes u x to the 1/2, or root x, and u prime is pop down, power down. So u prime written without a negative exponent would be 1 over 2 root x. The derivative of cosine of root x is negative sine u prime. Negative sine u, which is root x, times u prime, 1 over 2 root x. That's our answer. We're just going to clean it up a little bit by bringing this negative 1 over 2 root x in the front. Number 4 can definitely be a little intimidating. I'm going to rewrite tangent squared of x squared. If you have tangent squared, remember that's the entire quantity being squared. So tangent of x squared is all being squared. So we can bring this out to the outside. These are equivalent. Beginning from the outside in, we're going to use the general power rule because we have a function of x all to the power of 2. For general power rule, we're going to pop down and power down. Inside is u, and we multiply by the derivative of u, or u prime. For the derivative of tangent x squared, is this tangent of x or tangent of u? A function of x. It's definitely tangent of u because this is x squared inside. So u is x squared, which makes u prime 2x. The derivative of tangent u, so this entire thing will be done deriving after this step. The derivative of tangent u is secant squared u, u prime. And to clean that up, we'll put the 4x in front. Derivatives of exponential and logarithmic functions are as follows. The derivative of natural log of x is 1 over x. So the chain rule version is 1 over u times u prime, also known as u prime over u. The derivative of a number to a power of x, the derivative of a number to a power of a function of x, and then what about the derivative of e to the x? If you actually used a graphing calculator to graph y equals e to the x and the derivative of e to the x, you'd get the exact same graph. The derivative and the original function are the same for all x's. Another mind-blowing thing about the natural number e. So that makes the derivative of e to the u with respect to x, e to the u, u prime. Y equals natural log of 3x plus 1. Is that just x, or is that a function of x? That is a function of x, where u, a function of x, is 3x plus 1, making u prime 3. The derivative of natural log of u is u prime over u. Wow. Is this e to the x or e to the u? It is e to the u because our power has a function of x in it, making u prime 2x. G prime of x would be e to the u times u prime. I like to write it with the 2x in front. Here we have 2 to the x times x. There's a product. Let's identify f and g. The derivative of a product is f dg plus g df. The derivative of x with respect to x is just 1. The derivative of 2 to the x falls under this formula. A is the base of the exponent, 2. So this would be 2 to the x times the natural log of a, natural log of 2. That would be an acceptable answer. You could also factor out the 2 to the x, which does make it look a little cleaner. What about ln of x times e to the x? Now you may remember properties of logs, for which if you take the natural log of a product, it's the same as natural log of the first part of the product plus natural log of the second part of the product. If you're taking the natural log of something to a power, that power is undone by natural log. Natural log is the opposite of exponents. And so you get x times ln of e. What is ln of e? Hey, that is just 1. So ln x plus x is another equivalent way of writing this function. And then you could derive ln x plus x instead of deriving this. And you'll get the same answer that we're going to get, but I'm going to show you the product rule within natural log. So I have natural log of definitely not x, multiple things. So u is equal to x times e to the x, which makes u prime product rule. F times the derivative of g plus g times the derivative of f. The derivative of ln u is u prime over u. We can factor out an e to the x. And then we can reduce. Our derivative is x plus 1 over x. Or if you derived the other version we did, that would be 1 plus 1 over x, which is equivalent. For number 9, I'm taking the natural log of definitely u, some giant function of x. U is equal to sine of x squared minus 2x. What does that make u prime? This is a sine of, the derivative of sine of u is cosine u times u prime. U prime is the derivative of this, 2x minus 2. Y prime is u prime over u. Is there any simplifying we can do with trig identities? Yes, cosine of theta over sine of theta is equal to cotangent of theta. If you can ever use trig identities to turn something from a fraction into a non-fraction, absolutely do that. Similar to tan squared, when you have ln squared, that is just taking the ln function and multiplying it by itself. So natural log of x, that's going to be squared, and then we're going to take the cotangent of that. When we derive, we start from the outside in. So we're taking cotangent of u. The derivative of cotangent of u is negative cosecant squared of u times u prime, or the derivative of this ln x squared. All this stuff in the front is already derived. Now we're going to derive ln of x squared. Here we have a function of x to a power. So we're going to use general power rule. U is ln x, and I know that u prime is 1 over x. Pop down, power down. What goes inside? U. What do we multiply? U prime. There's my derivative.